Hi, everybody. Welcome. Thanks for coming today to see Ellie Pavlick speak. Welcome to the Digital Theory Lab, hosted under the generous umbrella of space and cooperation of the Remarque Institute. Thanks, Amy, for everything you're doing for this. And thanks also to the Open Society Foundations, which have provided funding for this public lecture series in AI, cultural AI generally. Look out for our big March conference, which is scheduled from March 9th to 11th, which we'll announce sometime this week. Today, we're welcoming Ellie Pavlick, who is the, do you say Briger?
Brigger, I think.
Brigger Family Distinguished Associate Professor of Computer Science, Associate Professor of Cognitive and Psychological Sciences at Brown University. Her research focuses on natural language processing, semantics, and pragmatics, in particular in the emulation of human styles of speech, language, communication, inference. I want to mention also that she is the director of the new NSF AI Research Institute, ARIA, which also involves Tal Linson, who isn't here today, but is our cherished colleague downstairs at the Center for Data Science here at NYU, and which focuses on the joint study of human and machine cognition and its implications for mental health and well-being. Ellie's research we became aware in the Digital Theory Lab of Ellie's research when she published a series of really profound mechanical, not mechanistic, sorry, but interpretability papers that questioned whether LLMs were able to perform a kind of deep formal semantics that extends back to the work of Gottlob Frege. And the answer was kind of, somewhat, yes, a little bit yes. And we were absolutely fascinated by these results. So we've wanted to talk to Ellie for a long time. This is not her first visit to NYU. At a separate visit, she said, I was on Zoom for this, but she made a huge impression on me with a wonderful comment that she made there was a sort of debate going on about could the language that LLMs use be grounded? You know, there's been this debate going on. Well, they don't have perception, so they can't be grounded. They don't have a world model. They don't see the physical world, so they can't be grounded. And Ellie just said into the middle of this conversation something like, I'm going to get this wrong, but
I don't remember.
This is how I remember.
Where is this going?
This is how I read it. I personally don't know the difference between an oak and an elm tree at a level of granularity, but when I say those words, I don't think they're ungrounded. This was 2 or 3 years ago. And I was on Zoom and I was like, seriously, I'm going to keep that example.
I think I got that example from somewhere. I won't take credit.
Yeah.
One of the foundational conceptual role semantics.
Okay.
But I'll take credit for it. If you want to say, as famously argued by Ellie Pavlick.
As famously argued by Ellie Pavlick.
You give me credit for all kinds of things.
Grounding doesn't occur because language is completely immersed in the physical world or something like that. And I was like, okay, so we really have to have a conversation with this person here in the lab. So we're really delighted to be hosting Ellie Pavlick today with this talk. We call this the humanities parenthesis. How does AI think? And so thank you so much for joining us. Please welcome Ellie Pavlick.
Yes, thank you. I'm very excited to be here, and I'm glad that's the background you're interested in, because I think this talk is very much in the spirit of the formal semantics, sort of, kind of, a little bit, but it's just like the couple years later iteration of it. So yes, I'm very interested in this question of does AI think? I think a lot of us are, like the whole world is kind of asking this question right now. And I am quite confident it is impossible to divorce this question from the question, how does AI think? That we can't really say whether or not AI thinks without knowing something about how AI thinks. And this is very challenging to get at for a number of reasons. And probably first and foremost is that we don't really know how humans think. So we don't really have a ground truth standard or metric of what we mean by thinking against which we can then evaluate AI. You probably all believe me that we don't know how humans think, but I'm just going to kind of belabor the point. So there's many different kind of places where we could start, and fields and disciplines for trying to figure out, well, can we characterize how humans think? So maybe we could start with the brain. It's a natural place to start. And even here, you'll start to see kind of the pieces of disagreements and confusion about what it means for the brain to be thinking, what the brain's even doing. So, for example, there is a lot of work on analyzing individual neurons within the brain, and there's very kind of exciting and really easy to point to results that are like, this is not a bizarre thing to do. So there's famously work that shows neurons that respond consistently to specific concepts. Jennifer Aniston was the example they used in their paper. There's like one neuron in the brain, maybe not everyone's brain, but the brain of the person they were studying that just consistently responded to Jennifer Aniston, whether you saw a picture of different types of pictures, heard her name, read her name, that kind of thing. And this kind of insight kind of leads to this idea, well, maybe that's all it is. Maybe all the different neurons correspond to all the different concepts or all the important concepts, and then we have connections between them, and they kind of create this connectome. And if we map out this whole connectome, we'll have it. Like this is the story of how the brain and therefore how human thought works. Um, and there is an active community on this. This is still it's going strong. But it's not as though everyone's like, yeah, that's how the brain works, right? There's a whole other view in neuroscience, which is, equally consistent with data that's being found, that says, no, the individual neurons don't really make sense. Don't bother analyzing them. What really kind of explains how the brain works is the kind of whole patterns over the whole brain. You should record the kind of wave-like patterns of activation over the entire brain. And in this kind of a space, we'll be able to differentiate different kinds of thoughts and concepts, right? And both of these things, there's, studies to show that both of them have good explanatory value for different kinds of things. So there's not a consensus of like, how does the brain work and what is the right way to look at it? So maybe the brain is too low level, maybe the brain is just a complicated, messy thing, and we should pop up a level in there we can get a better handle on a more abstract notion of how humans think, like maybe at the level of what we might call the mind. And then very much in the spirit of what Leaf was just referring to, like even if you abstract away over the kind of minutiae and the details and the weird biochemistry that's involved on the brain, there are very active debates about what is happening in the mind and how much does this matter or not matter for what we would call thinking. So on the one hand, strong views by some linguists and philosophers of language that the mind is really best understood as like a kind of container to represent the world. And the thing that matters is this representational status of the things that are in your head. By some other extreme, there would be like mostly what the mind is doing is kind of mediating between the kind of things we interact with in the external world and our goals and our intentions for moving through this. And of course, those are kind of straw man arguments, and most people would say it's a little bit of both. But the point being, there's not a consensus. We're not all in agreement. This is what the mind is doing. This is how it works, and that's what an AI would need to do in order to be equal to humans in that regard. And you could try to go up even higher and say, okay, we're not getting consensus about the mind or the brain, but maybe we can at least get consensus about what is like the important behavior, like the real behavior we should be explaining to get at the core of what humans do. And then even here, there's disagreement about like which behavior kind of represents what humans really do, how we really behave. Are we like these rational agents, the kind that produce music and do math and solve puzzles? Or are we these kind of heuristic agents that do things like commit all kinds of logical fallacies? This is the famous example from Tversky and Kahneman, where people report that somebody who is active in the feminist movement is more likely, or someone who has these particular qualities is more likely to be a bank teller and active in the feminist movement than just a bank teller, even though the conjunction should be strictly less probable than the single thing. So again, there's just like a disagreement about which one of these is real and which one is artifact, right? In terms of just the behavioral signatures we're trying to explain. And then this even stops short of like, this is all kind of assuming that we have this notion of an individual and we can characterize the individual that is the intelligent being. But of course, we live as part of societies, and there's a lot of notion, very much to the elm and oak example Leaf was referring to, where our intelligence is collective, and we wouldn't make sense to try to think about intelligence as just a thing that agents have, but it's a collective thing. And then there's disagreement about how much this trickles back. Maybe the mind is also kind of a piece of a collective intelligence, not an individual, something an individual even owns, really. And maybe your brain has a signature of this too. So there's this big, messy, complicated thing about what are we talking about when we're talking about things like intelligence and thinking in a human. And then we have to try to figure out how to measure AI against this complete lack of consensus. The question's even harder because we don't actually really know how AI works either, right? So we have some understanding. In some ways, we have more understanding of AI than humans. In other ways, maybe less. we know there are different components of the AI. We know there's the architecture, there's the thing we might call the actual model that you can load onto a disk or that's sitting there in a data center when you run API calls or talk to ChatGPT. And we know this architecture kind of gives rise to this latent space that kind of only exists in the moment when you're interacting with it. And then this latent space in turn produces behavior. And then there's some kind of feeling that we can map this kind of a thing maybe to something that humans are doing. And it maybe the most obvious thing is that the architecture is maybe kind of like the brain, and latent space is kind of like the mind, and then the behavior is similar behavior because we're interacting in language, for example, or dealing with the same kind of images. Um, but this is a challenging mapping to do because the AI is not really directly a simulation of human thinking. It wasn't designed to be that way. Um, and so even though there might be these kind of analogies we can make post hoc, there's also a lot more analogies, maybe too many analogies than we actually would want to make. So I just argued that this kind of latent space notion is also something neuroscientists talk about as maybe the right characterization of the brain. So maybe the latent space is more analogous to the brain than the mind, but it's also the case that language models kind of think in language in a very literal sense that isn't necessarily true of people all the time. So maybe that latent space actually is closer to human behavior in other kinds of ways. You can think of something like a reasoning model that will output tokens in words, right? And you're like, well, this seems more like a behavioral thing than a mental thing. And then this is compounded by the fact that the humans themselves have built or designed or influenced these different stages in various ways. And so again, we're left with this kind of messy space of trying to figure out whether AI is thinking by trying to reconcile it with what we might know or might not know about how humans are thinking. But everything here is kind of up for negotiation. The thing that kind of comes to mind when I think about this whole problem space is like if you've built like IKEA furniture and you like have to put in a lot of screws, and it's like don't tighten any screw all the way before tighten, like you do them all a little bit, because if you like crank one all the way, then it's going to move this whole cheap piece of wood out of alignment, and you'll never be able to make it flush because the other thing will be whack. So instead you go a little here and a little there and a little there, and you keep moving around and you do all the screws until the whole thing kind of stitches up. And I think that's where we are in this kind of world of thinking about thinking, is like everything is moving at the same time. And there's definitely like, it's got to fit together at some point, but the exact thing we're going for, you can't commit to any one thing without having to constantly reconcile against the others. So I'm very interested in this question of does AI think, or just what would it mean for anything to think? What does it mean when humans think? And we just can't possibly answer this right now because it depends on characterizing the internals of processing AI and on analogizing these to internal processes of humans. And as we draw these different analogies, like there's going to be some analogies where it's like an obvious similarity. We're going to say this is just remarkably human-like. It's kind of doing the same thing. It's basically the same process, one in silicon, one in the brain. And then there's going to be other cases where it's so strikingly dissimilar that people are going to be like, it's just like dead on arrival that you're even trying to anthropomorphize this thing. And you hear versions of both of these arguments happening in real time, right? Something that I've been just maybe have always known is true, but have been like appreciating a lot just in the past year is that the realization that there's not like one true analogy. Again, the AI is not built as a simulation of humans, and it's not as though it's not an argument about which one is the real one. Is the AI more like a collective intelligence? Is it more like an individual intelligence? Is it more like a behavior? Is it simulating these things? Like it's none of those things. It's just the thing that it is. And different analogies will tell us, we will learn different things from different analogies, but they are just different systems. And many of these things will hold simultaneously. And sometimes those analogies are inconsistent with one another. And I think this is this kind of crazy, exciting world to be doing research in. And as we're trying to make progress on this general notion of thinking and thinking about thinking. So I don't think there's any shortcuts here. It's just going to be a long, messy process of muddling our way through this quite interesting landscape of problems. So with that long intro, most of my time is now spent thinking about the how part. How does AI think? And I think about how humans think, but more often I think about how AI thinks, and I talk to other people who think a lot about how humans think. And while it is definitely true we don't know how AI thinks, or really how it works on a lot of levels, I also have like stopped using the phrase black box, because even though maybe when I first got into this area, maybe around 2018, when people like kind of the earliest LLM large language models were out there and people started asking what's happening inside, we really felt like we had no idea what was happening inside. But now we're like not quite a decade later, and I think there's pieces, right? So we kind of starting to have a picture emerge. It's not a full theory, but there's kind of themes that we're seeing pop up, and I want to emphasize some of the what I think are the really important ones that are unlikely to like go away as we poke more. Um, one of these is the notion of structure, and I'll spend probably two-thirds of my time talking about structure because I think structure, the emergence of structure is so fascinating, particularly because of the role it's played in the history of thinking about language and cognition, and because of the fact that neural networks have frequently been assumed to not have much structure. So the kind of thinking that the AI does is deeply structured at a couple different levels of defining that structure. But it's also extremely context dependent, and I think these kind of stand in contrast with each other in a certain way. They're not like incompatible with each other, but they're often talked about as though more structure makes it harder to be flexible to new contexts. And the neural network, the AI we have right now, has shown a really interesting way that these two things kind of live together quite harmoniously. So like I said, I'll talk for about two-thirds about structure, about a third about context dependence. Um, so like I said, I've been fascinated with the structure question probably since I've been doing this kind of interpretability work. And this is because coming from a background with an interest in things like linguistics and semantics, like structure is like the name of the game. The thing that makes these domains so interesting is that we believe they are very richly, hierarchically, compositionally structured. And neural networks, when we depict neural networks, we just think of them as these big amorphous blobs. This is like one of the first pictures that come up if you search something like neural network, right? That's like dense, evenly distributed all over. There's nothing like it's kind of beautiful in a certain way, but there's not like but it's just like a big smear of activity, right? And so these get contrasted with what we would think of as more structured architectures, which can vary in how rigid they are. But we can think of things like the logical kind of computational systems, things like Turing machines, formal logic that are quite rigid. But even things like the human brain, when I talk to neuroscientists, like one of their main criticisms of AI is that AI is too like homogenous, right? The brain has specific regions that have different kinds of architectures for different types of tasks and have evolved with different pressures. And the neural network is just a giant flat thing. And so how could these kind of be the same type of a system, right? Um, so the thing that so when we think about structured neural networks, we're kind of contrasting against this view that they are just a big amorphous blob. And there's really two ways in which we're seeing that that's not true. That's not a correct characterization of the systems that we're interacting with right now and finding so impressive. It might have been a characterization of them kind of in their initial state, but by the time they're producing the intelligent behavior that we see, they have a ton of structure. And one of the levels of this is structure just at the level of the architecture itself. And when I talk about architecture, this is like the weights that are stored on disk, or what we think of as like the wiring of the neurons, right? So there's a lot of examples you can point to illustrate that there's this emergent kind of structured architecture. I think the most compelling is this stuff that's come out of this general area of mechanistic interpretability. It's kind of the sub-discipline or the buzz phrase these days that kind of works on this particular way of analyzing how AI thinks. And so there was a now famous study by Wang et al., and this was a couple years ago, maybe 2023 or 22, something like that. And what they're looking at are the kind of particular architectural components that after the model is trained, work together to perform a simple task. So here, this is a language model. It's trained to predict the next word in a sentence. And so the model gets something like Matthew and Robert had a lot of fun at school. Robert gave a ring too, and it's supposed to say Matthew here. And if you know about kind of current AI architectures, there's these things called attention heads. If you don't know about it, it doesn't matter. They're basically little groups of weights. And what they're finding is these heads, these little groups of weights, specialize to perform kind of pieces of the algorithm in order to predict the next word here. So specifically, they find one of these heads that finds duplicated words in the sense that I just noticed that it has heads, which is funny because it's the duplicate token. And I've given this slide like God knows how many times. I've never noticed this before, so interesting. This is in the context of a new talk, and suddenly I know this is like context specificity thing. There's something deep there. Anyway, very meta. Yeah, so one of these heads basically recognizes when a name has been repeated. Then a later head basically blocks subsequent attention to that repeated token. And then a third head or group of heads basically copies. And in this case, it copies names. So you can say that the algorithm that the language model is running here is like, say a name, don't say the thing that's been duplicated, right? It's not a linguistically rich algorithm, but it's a one that will produce a correct answer in this case. And it's also a interestingly like structured one, right? There's these little pieces that are doing parts of the task. It's not just a one-shot mapping from the whole sentence to the answer, Matthew. And so this, when like I first saw this, was very exciting, kind of a notion. And but then the question becomes like, is this like a cute thing that you can pull out for a particular example, or is this really a window into kind of the building blocks of how language models are working on an architectural level? So we've been doing a lot of work on trying to find out how reproducible these, not just this general idea, but these specific components are in performing very different types of tasks. So for example, we look at a task that's very different on its surface here. The model is supposed to look up or retrieve the color of of objects based on a list of objects. So it has nothing to do with names. There's no proper nouns. It's different on its surface. And if you figure out what kind of algorithm it's running under the hood, you can find the same duplicate token head performing the task of identifying the duplicated word here. There's this middle component that's actually different than the inhibition. I'll come back to it. So it doesn't really do this inhibition step. Instead, it kind of promotes attention. And then the same mover heads that previously were copying names are now copying colors, and they copy the color of the duplicated name. And so you see this kind of 2 out of 3 of the pieces of this algorithm are identical, like the exact same thing, performing in the same way. And then this middle section is different. But it's actually one of these things where the fact that it's different turns out to be a nice feature, not a bug for this experiment. Because if we look at the performance, just the model's ability to retrieve the correct colors here, it's very bad. This is a fairly small model that we were working with. So this model is great at knowing who gave the ring to who in those earlier examples, but it's terrible at retrieving colors. And one of those reasons might be because it's failing to do the correct inhibition. So we can kind of rewire and just say you should use that same inhibition head that you were using in this other component, and you can see that that recovers the performance. So it makes this point that like there are these little blocks and they kind of perform these little functions that are somewhat independent of the task they are doing when they perform that function. Like detecting a duplicate is just detecting a duplicate, and something later downstream can use that information, and the duplicate head to a large extent doesn't care what's going to happen to it downstream. Again, to a large extent, not exactly, but we'll come back to that kind of idea. And these heads reproduce in these same kinds of ways in a remarkable set of circumstances. So we even found that the exact same things emerge on different models trained in different languages. So here we were looking at monolingual models, so English and Chinese, and there's really no word overlap that would cue to the model that these should be analogous, right? So usually we think about models as exploiting similar words in order to recognize similar structures or similar concepts. In this case, we don't have that kind of word overlap, but we do have similar syntactic structure, in this case, between English and Chinese. And as a result, they get handled by the same kind of, the same architectural components internally. We also have been looking at how this works across tasks. And this is a little bit different because they're not the exact same components, because they're kind of a functionally different thing we're asking it to do, but it's similar flavor of specialized heads performing specialized routines. In this case, we're looking at, for example, when you ask a model the same question with different kinds of prompts. This is something anyone who's worked with language models, this is a common source of frustration, is they vary depending on how you ask. So like if I want to know the company that made a product, I could just ask, what's the company that made this product? Or I could give these kind of examples, this what we call in context examples, right? Siri is to Apple, as Gmail is to Google, as Bluesmobile is to, I guess, Dodge. And we find here similar, there's like particular heads that independent of how you render the task in the prompt, the same heads perform the task. And this is interesting because again, there's no word overlap between these prompts, right? They don't actually contain any tokens in common to cue it to what the kind of relation it's trying to perform is. So the kind of these points on kind of focusing on this idea of structure at the level of architecture. This is like how are the little components in the weights wired such that they talk to each other in such a way to perform more complex tasks. And here we see a remarkable amount of structure that emerges once the model has been trained, but wasn't there initially. That looks like a more like one of these more carefully engineered systems that might have tried to build in specialized components to these types of things. But I like this was exciting when we first started working on this. Uh, this is a very exciting notion. And so there's been a lot of focus on trying to characterize these weights, but it would be like a mistake to focus or just focus exclusively there because there's actually also a remarkable amount of structure in the activation space that gets kind of created when these weights compose with particular inputs. So you can think of the architecture as being like the machine that manipulates a representation, and this latent space is the representation being manipulated. And here too, we have a lot of structure and arguably more important structure for understanding how the AI kind of is thinking about the world. So we've actually known for a long time that these kinds of latent spaces, in particular, the ones that you get out of modeling text or modeling rich aspects of the world, contain a lot of latent structure. And a really famous example of this is from the Word to Vec. So this is 2013 paper on just vector word representations that you get out of text. And the kind of this is like the picture people have in their head when they think of word to vec, which is that you get this structured geometric space where the model knows that basically woman and queen are similar in a certain type of a way, and queen and king are similar in a different type of a way. And in fact, the kind of the geometric relation by which woman and queen is similar is the same as the one by which man and king are similar, and similarly woman, man, queen, king. So you get this kind of analogical structure within the geometry of the space. And this is really exciting, and people have been very interested in how you can use this kind of to represent the space between lexical concepts. But what's been so exciting in large language models and current AI systems is that this similar kind of an idea extends to much more abstract concepts, including the representations of things like tasks and functions that you might apply to things like clusters of words, right? So I'll use an example from a recent study. There's a lot of examples we can use to illustrate this point because it's really blown up as a thing that people are very interested in this structured latent space. But I like this example because it feels so far removed from the like king, queen, man, woman type of a notion of concepts. So here we're looking at again at multilingual setting, and we're looking at multilingual question answering. So models that are trained even in multiple languages will show huge performance gaps between English and other languages. So here you can see it for this is like simple factual recall tasks. It's somewhere in the 60% on English and as low as like 2% in Chinese. And so what we can try to understand is what's happening internally in the model when it is trying to answer this question in this case, French. And so we have, I'm skipping over the details, but we have reason from our work and prior work to believe that what the kind of internal pipeline the model is doing is it's basically taking this French, translating it into English, looking up the answer in English, and then translating it back to French. And so one type of error that could be happening is that the model knew the answer, but it failed to translate it into French. And so if this were the case, and this is where we'll go to this structured representation, we would say, well, maybe if the model knows how to translate, we can fix the translating without having to do much else to the model. And in fact, the model does know how to translate. If you just ask the model to translate Buddhism into French, it gets it correct. And so what we want to do in this case is we say, okay, in the context where the model is correctly translating a word into French, there's some direction in space that corresponds with like the state it is in when it is doing a good job translating. And we can pull out this space similar to this kind of man, woman, king, queen direction. That's what this little vector is. This is like the translation direction in space. And this is going to be generic. It's not specific to translating the word Buddhism. It's just a generic translating direction. And what we can do is we can take the time when the model is trying to answer a question in French, and we can just inject, kind of push the whole space to say, move more in the direction that you would be in if you were translating. And when we do that, we can see that we get big jumps in the performance. So this seems to fix about the percentage of errors we were estimating were due to this kind of a thing. So this suggests that, again, this is like a generic translation direction that when added into this question answering task, fixes at least some non-trivial chunk of errors for retrieving the correct answer in another language. A similar thing happens, a different kind of error might be that the model actually just didn't know the answer or failed to retrieve the correct answer. And here we can see this again is the case that the model actually might have retrieved the correct answer if we'd asked it differently. So the models are very good at doing this pattern matching thing. So maybe if I say, what is the main religion in Thailand? It doesn't know. But if I do this, Italy, Catholicism, Turkey, Islam, Thailand, now it knows. And so the same idea is we can say, well, let's figure out kind of what is the general direction that the model is moving in the space when it gets this right. And let's pull that out. And then let's inject this in again in a kind of generic way, again, not specific to looking up religions, definitely not specific to looking up religions of Thailand, but just the general direction of doing this type of a task. And then again, you get these big jumps. So the point of this example is to say that we have these kind of very simple operations we can do that basically corresponds to like adding these vectors, adding these directions in space, not unlike what we do with the king, queen, man, woman direction, but suddenly in a way more complex space where rather than saying I'm adding something like gender or royalty, I'm now adding something like the space of doing this task. And I can plop it into a kind of new context and it makes the model do the task and it kind of gels with the other stuff in the correct way. I like this example because it's kind of, you can see how this works in a model kind of in some end-to-end task you're trying to do. But like I said, this like interest in, this is often referred to as steering in this latent space has become really popular just in the past little bit. I don't know. I've lost all sense of time. Like it could have been the past month, past year, past week. I don't know. Some recent time, people have gotten very into this idea. And it works for all kinds of tasks that we would think of as capturing these really more abstract things that we refer to when we talk about things like cognition and philosophy of mind. So, for example, one of my students was recently working at this idea of like event modalities. So there's directions in space that differentiate between things that we would assign zero probability in event space. So something that is an impossible event, like chilling a drink using fire, versus something that is just an inconceivable, like a category error, like chilling a drink using yesterday. These are both zero probability kinds of things to say in some possible world, but there is a subspace that will kind of differentiate between one of these is a zero probability because it isn't going to happen versus one of them is an zero probability because it's like a category error. There's been work from, this is a paper out of, I forget the group, I think the AI Safety Institute, like Dan Hendricks and all, on this idea of representation steering, and they point to things like part whole structure in vision models and even like truth and falsity. So whether or not a model is being honest or dishonest in a conversation similarly has this kind of directions in space steerable property. So something I find almost as probably even more exciting than just the presence of these directions is something that is specific to the directions in the context of language models that might like we find this structure in things that aren't language models, but I think there's something unique to how they work and maybe why they're so effective in language models. And it's that they can often be quite literally lexical in nature in a way that's kind of weird and interesting to me, and I'm not entirely sure what to make of it. But so we are kind of emphasizing that what's interesting is this geometric structure that, there's a relationship between woman and queen, analogous to king and man. And that you can capture this relation as a direction in space. But it's also the case that this is a lexical space and words are just directions in space. And so it might be the case that this vector is literally the word royal, right? Like this is just a direction in space and it has a lexical value. And what we find in these language models is that at least sometimes this is true, that these kind of directions in space themselves are words that decode to semantic meaning. So when I use this example of the kind of cross prompt case. So here we have different ways of asking the model to produce the company of a product, and you can find these attention heads, these little components that consistently are activated when the model is trying to do this company retrieval task, for example. But what these components do is they operate on the latent space and they move it in a certain direction. And if you just say, find that direction that they're moving it, and what word does that decode to? If I just force it to be a word, it'll just say the task that it's doing, right? In a kind of like in weirdly interpretable kind of way that feels like it doesn't have to be the case. So if you're trying to find the capital city of Japan, the direction that it moves is the direction that you would use if you were just saying the word city or capital. If you're trying to pluralize a word, it'll say things like multiple or plural or several. If you're trying to find an antonym, it'll say things like opposite or reverse, right? And this kind of lexical form of language, like you can see models kind of thinking in language in a way that's just very convenient for us, but also kind of gives the insight into the kind of structure of their internal space. So we've also looked at these kind of functional factual retrieval questions. I've kind of been using this idea. So you say like it's the capital city of Beijing, or what's the capital city of China, and the model says Beijing. And you can think of this as some function like A of X goes to Y. And if you look just over the layers of the model, because this is kind of one way of representing like time in the model, like how it's going through some thought process, each layer builds on the next one. Um, by the time it gets to the end of this and outputs an answer, it's obviously saying Beijing and thinking about Beijing, like the space is aligned with Beijing. But interestingly, prior to that, you'll see a peak in China. So it kind of thinks about China before thinking about Beijing in order to go through this process. And this reproduces across a lot of different models and different sizes of models and different types of tasks. And I think more interestingly, it, at least in some cases, extends to more compositional notions of this task. So now I can say, I want to know, I have some function, but that function is defined as like A of B of X, right? So I want to know the capital city of the country where the Yellow Mountains are located. And in this case, the model can, in principle, a neural network could just map directly from Yellow Mountains to Beijing. There's nothing that really prevents it from doing that. But instead, we actually find that it will think about this intermediate Z value on the way to getting to Beijing. So you can decode some region in the middle of the processing where the word China is kind of the primary direction that it is, that its head is aligned with before switching to Beijing. So you can see this kind of signatures happening of this processing, and it kind of lives in the space of words and lexical representations. So kind of stepping back on this issue of structure, um, like I would say that just a consistent finding across many different aspects of my own work, but like everyone else who's been working in interpretability for the past 5, 6, 7, 8 years, is that it is extremely structured. So far as I'm comfortable saying that AI thinks using structured representations, right? Um, the and this structure emerges, and it's like very much happens at the same time that the models learn to do more complex tasks. Like we don't have good examples of models that are succeeding at the complex tasks and do not have this kind of structure. Um, and I think it's important and very interesting that it exists at multiple levels. So the architecture itself, the weights, kind of rewire in a way that shows kind of functional specialization and reusability, these kind of little modular building blocks. But also that architecture is manipulating a latent conceptual space that is also richly structured. And I actually think the kind of simultaneous emergence of structure on both of these things is important and interesting and worth and is like a direction that we're exploring and people should be exploring more, because it's not that they're like a one-to-one mapping, like they're related, but they're not the same structure, right? I also think this kind of, so like I said, this kind of intrinsic connection between the structure and the representations of the architecture. And it also calls to mind a very analogous debate that is happening in neuroscience right now about why do we see this kind of structure in the kind of connectome, but also in the activation space, and which one of these things is primary? Like which one is the better way of understanding what the brain is doing or understanding what AI is doing, which really points to kind of general research program and principle around trying to figure out how do these things work together, and are there kind of general principles that constrain any kind of intelligent system we would call intelligent, that we would see this kind of simultaneous structure emerging at multiple levels, or is it coincidence, or is there some other reason that we're seeing this happening? All right, so I'm going to end on structure. This is kind of a more than midpoint pause. I think I'll just go through and then do discussion after. Usually I like to pause for questions, but I think this is more better if we just throw everything out there and then just take it on. So, So I'll switch to this issue of context dependence. I debated with what to call this. I had flexibility, but I feel like flexibility wasn't quite the right thing. Um, but I think context dependence is probably the important piece that I'm trying to get at here in what I think is this clear part of how AI thinks. So, but it's meant to be kind of to stand in contrast to this structure argument. So, like I said, I've been fascinated by structure, and most of my interpretability work has been about things like structure to such an extent that I often give talks that really, and at various points, I've like argued really what we're seeing here is a neural implementation of what is latently a symbolic system, like our symbolic AI systems of yore. Um, and I definitely have made this argument, as have many others, this kind of idea that maybe there's this kind of, we can pull out this emergent source code. So this is like actually a figure from a grant that I currently have. I was at the PI meeting for yesterday where I was kind of promising to do this. Like say, we're going to go in and we're going to analyze these weights and we're going to pull out this kind of interpretable symbolic structure that describes what the neural network is doing, but gives us kind of handles and hooks into what it's doing such that we can manipulate it in a way not unlike what we would do with traditional code. And wouldn't this be amazing because we would have all these safety guarantees, we would be able to just know what it's going to do, which is something we can't do right now. And I think there's been this general feeling after seeing some of the results that we're seeing that like maybe we can do this. Very much in the spirit of this kind of human connectome project. Like we get these promising early results and we're like, maybe we can go all the way, right? I think this line of reasoning is very famously credited to Chris Olah in his circuits thread, this idea of reverse engineering the source code. And he makes this argument fairly explicitly in that thread and elsewhere in his talks. But the problem then, after trying to do this for even a little bit, is this like, it doesn't seem to really just be a latent symbolic system. And maybe people who didn't jump on this bandwagon were like, yeah, we knew that all along, but it was worth testing, right? And I guess it hasn't completely been ruled out. Like there's actually in the discussion, it's worth maybe talking more about like I still think we don't know exactly what's going on here, but it's very clear that there are patterns that make it very, very hard to do this. And in particular, it's that these circuits, these kind of symbols are weirdly interlaced in a way that makes it hard to not only describe them, but also to even measure them, right? So we have a work in progress. So this is kind of a fresh example, but I really like it for a number of reasons. So I use it to illustrate the point. Um, so this is using reasoning models, and I like reasoning models because they're like, if anyone, if anything should be a symbolic system or like a neural implementation of a symbolic system, reasoning models are really trying to do that, especially when you apply them to math. So what you do in a reasoning model, and this is what most of the state-of-the-art systems are right now, is you give it some input like what is 111 plus 435, and it will produce a series of tokens that gets you to the answer by breaking it down into steps. And it gives you an explicit chain of steps here. It breaks it down into the hundreds, the tens, and the ones digits, and then it adds them together, and then it builds them back up, and it gives you a final answer. And so this is something where like not only is the format, but also the domain is such that like a symbolic algorithm could do this. Like if you have in your head the kind of old school Turing tape that's copying and moving things around, like that would succeed here, right? And we know from the kind of architectures of the attention heads I was just talking about, that they have things like copy heads. And in fact, we have good reason to think that in a normal case, like what you would see here is the model look back at its own thinking and just copy the final answer to the final state, which sounds great. So what you would expect then is if I go in and I change it to say 547, it should copy the 547. And I would expect that in the usual case it says 546. When I change it to 547, it should say 547. What actually happens if you do this is that it's about 50-50, almost exactly 50-50, 49-51. And I think this is fascinating to me, not just that it doesn't switch to 547, but it also doesn't always stick with 546. So this really epitomizes this weirdness of it's not like the model is directly in this causal relationship that you want it to be with its reasoning chain, but it's also not in that relationship. Like it also sometimes does change in the way you would that you would expect. And so something else funky is going on where maybe there's multiple mechanisms such that sometimes it's kind of using its chain in the right way and sometimes it's in the wrong, or using something else to get to the answer. And one thing we could imagine is happening is that the system gets into this kind of weird, funky state of saying like it's actually like, this chain doesn't even make sense because it has an inconsistency. And so maybe it's just confused and it kind of represents these things as equally probable and it's flipping a coin and that's how that would get you exactly 50-50. And this is a reasonable thing to think. Um, but that's also not what's happening. It seems to be the case that on a given run, it's fairly confident in which thing it's going to say. So it's not actually representing these as equally good answers on a given run, but from one run to the next, it changes which mechanism it prefers to use. Is it using its chain or not? And so this creates this kind of interesting, weird puzzle, I think, to me, because like this doesn't look like what you might expect in something like our more traditional systems where maybe it's marginalizing over multiple possible mechanisms that could use and they average out. It's like it's kind of committing, but it's committing in a way that feels very idiosyncratic and probably dependent on features of the input that we're not even really sure what they are. I'll also say there's an additional constraint here, which is it seems to change as a function of having intervened, right? So by virtue of kind of messing up the latent space in order to try to get it to change its answer, you also change the kind of mechanisms it's using, right? So we're exploring this more. So we don't know exactly what the features of the input are that cause it to fluctuate between these in this particular case, but we have other studies that kind of hint at what we think the kind of uh, ideas and concepts that might be in play, which is just this general idea that the way that the AI is going to think is going to depend on what it's trying to think about. Um, and this is also true of humans. So humans have this kind of input sensitivity um, in a in a kind of similar analogous kind of way. So for example, there's a study from Decker et al. This is from kind of the realm of cognitive neuroscience, where they're asking people to do this compositional generalization task. So here you have to place colored animals on a grid. And one thing you can do is you can show people like all the yellow things and then all the fish. And then they do a really good job at doing this compositional generalization of saying like, oh, I guess columns refer to or are colors and rows are animals. And so I'll put the blue owl at position 1. But then if you give them the same amount of information, strictly speaking, but it's kind of scattered around so that the structure of the grid is not very transparent to the person, then they do a pretty bad job figuring out where where the owl goes here. A very related result shows a similar kind of a principle where you can say, we're going to try to teach people to differentiate between this blue concept and this orange concept. And if the boundary between the concepts is such that this kind of nicely aligns with features that are readily available to a human, things like short versus long, they'll do a great job. It's actually, to me, seems interesting, relevant that we think of these as maybe verbalizable concepts I can easily put into words. Not sure if that's important here, but it feels kind of related to other themes, throwing it out there. Whereas if you kind of draw the boundary on a diagonal here so that it's kind of hard to articulate what is the difference, people don't do as good. And in particular, they don't like if you show them a lot of blue ones and then a lot of orange ones. Instead, they want a random interleaving of blue and orange until they can kind of get like a gisty understanding, but they won't have to try to get a specific rule that differentiates blue and orange. So for humans, you see this kind of what you would call input sensitivity, kind of the mechanism they're using to make a decision or reason about it depends on all kinds of peculiarities, not just the exact input you're giving, but the particular way that you're presenting the examples and what other kinds of things might have happened, how loaded their working memory is, all kinds of features, right? And I can say neural networks have this, like the argument we make here is that neural networks can easily account for this kind of variation because neural networks also have this kind of different types of mechanisms that kind of interplay and coexist with each other. In particular, here we're highlighting just the difference between the in context, what we call in context learning and in weights learning, which is similar, I would say roughly analogous to what we're doing in the reasoning models, the kind of reasoning tokens versus the kind of latent in weights reasoning. And what happens in this kind of disconnect between the in context learning and the in weights learning is that basically you have these activation space and you have the weights that produce the activation space. And what happens is you have the weights plus the given input produce some pattern of activations. This yields some behavior, which results in some reward or loss. And then this goes back and updates the weights. So these things are not like really separate, but you can kind of imagine them as like two faces of a coin or two planes or something. But then once the model's gone through a lot of training, then once it can like figure something out, once the activation space is nicely structured such that it's easy to figure out what it's doing here, it no longer goes back and updates the weights, right? So you get these kind of two pieces of learning or reasoning or thinking or mechanisms, whatever you want to call them, where the kind of in context learning is often kind of it's exploiting like known patterns or what we might call rules from the training data, stuff it's gotten comfortable with and can be nicely structured. And as a result, it can act in a way that's kind of systematic, kind of compositional, at least appears that way. But the default weights learning doesn't really have that property. It's still primarily associative, idiomatic, and it can memorize individual contexts and their individual quirks if it needs to. And so we can show that this interplay can nicely explain the kind of idiosyncrasy that we see in humans. So for example, when you give it the nice thing that humans do a good job generalizing compositionally, in context learning just crushes it. It can do this. It knows where to put the blue owl, no problem. When you make these small changes, if you shuffle up the way you present the examples, or if you rotate the grid in a weird way, then performance drops precipitously, right? But of course, the model, it's not like the model can't do these things. It can figure out how to do them if you allow it to kind of go back and keep training. It can figure out and learn some new particular specialization for the rotated grid. It can figure out how to deal with the interleaving examples, right? So it's the model kind of has the overall capacity to handle these different kinds of inputs and different kind of learning regimes, but they kind of naturally go to different parts of the learning and thinking mechanisms. So we have this kind of so I made the first part of the talk kind of arguing that the structure is very essential to how AI thinks, and I think that is very true. But despite where it feels like that line could be going, which is that we should really be thinking of these systems as like these kind of latent symbolic machines, that I think that would be a mistake because the symbolic stuff is actually emergent, and really the main way that the AI thinks it's this in weights learning, this kind of idiosyncratic context specific learning, of which sometimes this structure emerges, right? So there primarily are still the big neural networks that we know and love and often criticize for lacking structure. And I kind of like to say the catchphrase here is like the exceptions are the rule and the rules are the exception, right? Like if they could do all of this complex stuff by just memorizing every individual thing, I think they would be happy to do that. The fact that they don't is because you can't, right? Like you can't actually do all the stuff we're asking them to do by just memorizing all the stuff. And so they kind of pull out pieces where there is structure and consistency and systematicity, and they work as such in that way. But then they can always fall back to their more idiomatic processing. A thing that I think is really exciting about this view of thinking about thinking is kind of starting to get away from what we often think of as a more stark dichotomy between associative reasoning and structured logical reasoning, but we're rather just like thinking them of different kind of features or properties of what is fundamentally the same process. And I'll say more about this in a minute. So kind of stepping back, how does AI think? I think, well, does AI think? Well, if we want to know if AI thinks, we have to know how it thinks. And converging analyses over just a range of different types of studies make it clear that AI's internal processing, we don't have like a full theory of what it's doing, but it's definitely highly structured, and it's also definitely highly context sensitive. So what we really need is kind of theories and principles that span these different levels of representation. So spanning the weights and the activations and the behaviors, what we might call the brain and the mind and the behaviors, but also train things like training and inference. So spanning the different kind of ways in which we can view these systems. And we would also need these to kind of encompass both human and AI thinking. We're looking for theories and principles that would kind of unify or push apart how we talk about systems that have certain kinds of behaviors. Like I said, this analogy to human thinking, or it's important to remember that AI is kind of an analogy to human thinking, but it's not a simulation. So as we're kind of figuring out what's going on here, it's just going to be the case that depending on where we draw these arrows and what piece we're looking at, we'll get contradictory results. It's going to be very human-like in some ways and very alien in other ways. And there's some places where it'll be kind of a category or just doesn't even make sense to ask this question or to try to make the analogy, right? And so I want to end on this kind of idea of being parts of the same process. Like there's like this, I was trying to figure out, I was trying to get Gemini to help me track down this quote because this is an example of I heard a quote. I don't remember who I heard it from, but it was something like the fact that there's a continuum between green and blue does not mean the whole world is a homogeneous shade of GRU, right? And I love that, and I've always loved it, and I have no idea who said it, but it's a great one. And then AI helped me create this beautiful image. But I really like, I've been thinking about this kind of because it kind of resonates to the general problem space, I would say, in two ways. One is thinking about the structure of the mind of an AI, and I would argue probably similar to a human, which is not as though we have um, uh, these kind of, which is this richly structured representational space that is kind of at the same time continuous in places and then peaky and discrete and might appear structured and symbolic like in other spaces. And these aren't like two different minds, right? It's all kind of part of the same thing that just has both kinds of properties in it. But I also really like it kind of on this meta program level because I think we often, when we're talking about the mind, we put up the two straw men. There's like the associationist neural network, and then there's the logical rational agent, kind of symbolic processing. And we kind of say these are the two options. And then they're straw men. And probably for the past many, many decades, no single person worth their salt has actually been either of those things. So we've all just said it's probably something in between, but this is where it's like, but that's not an answer, right? It's not all GRU. Like there's so many different in-betweens, and we're trying to figure out which of these in-betweens it is. And I think that's a like progress that hasn't been appreciated so much recently in the current AI moment is like we can agree that it's somewhere in between, but figuring out the exact nature of how these systems are trading off or superimposed or emergent from or reflective of one another is all kind of the weird GRU that we're trying to sort between. I think this is yeah, rich and complicated and going to take a while to navigate, but very exciting. So that's where I'll end. Thank you very much. And I will happily take questions, but I do want to plug ARIA for 1 second. So I'm just going to say it so I don't forget once we get into questions, which is just the institute that Leif mentioned. I just want to throw it out there because this is a new research institute that's very much in the vein of the kind of stuff I'm talking about, but also with connections to humanities, or broadly, in particular, mental health and well-being. It's an NSF-funded institute. We're like launched very recently, so we just have like a stub of a website. But if this audience probably cares about the things we care about, so you can go to the website and sign up for a mailing list, and then you'll hear about other stuff from me and all of my amazing colleagues that are part of this. So, all right. So now I'm happy to take questions. Thank you.
I have a question.
Yes.
I'm gonna use the prerogative. I wanted to ask you a little bit about the phrase like a neurological development of a symbolic system, or I'm not sure exactly what something like that, right?
Yeah.
Implementation. Yeah, neurological implementation of a symbolic system. And I'm wondering, I mean, kind of wondering what a symbolic system is in that, because I thought I knew you sort of mentioned expert systems, you mentioned symbolic AI, right? Oh, by the way, I think GRU is Nelson Goodman. Yeah.
Isn't it?
Isn't it? It's from the inference essay.
Okay.
Anyway.
I would love to know.
Yeah.
Claude couldn't find it for me.
Really?
I said, someone said this, and it was like, a lot of people talk about GRU. I was like, but this kind of, anyway.
I think he invented the term.
That'd be great. Okay. That'd be
Okay,
great.
but so I thought I knew what that was as you were saying it, and then as you showed the example with 546 and 547, I started to think like in a reasoning system, if you had a neurological implementation of a symbolic system, you would expect it to learn arithmetic almost first, in a way that it would be like not necessarily first, or it would learn, you know, as you were saying with those structures, like you might expect those structures to match symbolic systems that we know about really neatly somehow.
Yeah.
And yet we don't see that.
Yeah.
And what we do see, which I think when you were discussing the color differentiation example, that I'm not sure if those were based on reasoning models or not. But sometimes when you ask reasoning models to do tasks that involve arithmetic, but only implicitly, like you say, like, you know, you have to count some syllables or whatever. There was recently an Anthropic paper about like line length. right?
Yeah,
Where, how does the model
Yeah.
decide where to break a word
Right,
at
right,
the
right.
at the end of a line,
Interesting.
or which word is last on the line? That you get these kind of like, they're sort of casual arithmetic things that we do on a regular basis, you know?
Mhm.
And, but those are not, they're not like strict symbol
Yeah, yeah.
systems in a way,
Yeah,
you know what I mean? So I was
Yeah.
I was just curious if you could like think
Yeah.
a little bit more out loud about like what the symbol, because
Yeah.
it's not like a symbol, like a physical symbol
Right, right.
system in the sense of like,
Right.
you know, like Simon and Newell's
Right.
idea of like basically a computer
Yeah.
architecture that runs rigidly across a whole space like that,
Totally.
right? Yeah.
Yeah, and I think this is a bit where it's like why it's useful to say, like, I feel like the alternatives we've had have been pretty strawman in this way. Like I've been interested in symbols and symbolic stuff. And yeah, I don't have a good definition. And I used to think this was a me problem, but now I'm saying it's a them problem. Like, I don't think anyone has a definition. So what I have decided is a lot of this traditional symbol system stuff, basically, they don't have a definition. They have an example. They're saying this is a thing and this is symbolic. And that's not helpful because that is that thing. And if we're trying to ask, like, the human isn't that thing. So tell me what would a human need to do for this to prove this thesis correct, right? And what it then boils down to is a lot of kind of behavioral patterns of things. And actually we have with like Tom Griffiths, Tom McCoy, Brendan Lake, and Taylor Webb about this called Wither Symbols. That kind of makes this point that it's like most of what people are have pointed to as evidence that the mind is probably symbolic are these behavioral things that now the neural nets capture. So this goes back to, so then it's like, okay, so what actually, like, what are the symbols? Where are they? And I think this is, and this interesting nuance I would like to see us kind of get at. Yeah, I think that they're not going to be at all symbols I mean, they're definitely not symbols in the physical symbol systems. And they're not even going to be symbolic in like in what I said, like a neural implementation of a symbolic system. This is like, it's not going to be that because it's just not going to have the other properties of, like, it's not going to be behaviorally equivalent to a symbolic system, right?
Can I ask a behavioral question too? This is just one follow-up and then I promise everybody. Like I was very interested in the kind of neurological structure, behavioral science fix that came up a number of times.
Yeah.
And I was thinking like in the I can you say something more about that? Like, do you think that whatever is discovered there will look like a series of heuristics? I feel like this is a very tempting idea for people, but there's a funny way in which, like, because you said about your neuroscience friends at the beginning, right?
Yeah.
And there's like a modularity sensibility that we have about the brain, but my understanding is that I'm like not a neuroscientist by any stretch of the imagination, but my understanding is that we really don't understand how the structures relate to the global thing that the brain is doing. And the result of that is almost that like the Kahneman and Tversky stuff that you were drawing on has taken like, it's sort of like stretched a bunch of metaphors about, I mean, they're analyses of things that we actually do. That's not, I'm not questioning that, but it's often suggested that heuristics are based in the brain somehow. But I'm not aware of anything that proves that.
Right.
So and Anthropic does this too, just to harp on them a little bit. Like they will go like, it looks like we're having like intuitive leaps of judgment that are happening in here. And I'm like, maybe, but like you said at the beginning, like we're kind of like trying to explain an unknown with an unknown in that case. So
Yeah. I mean, I guess probably I would, like, if I had to say, does it look like all heuristics or something else? Like, given the language we have right now of like heuristics versus what's systematic, symbolic, or logical reasoning, I would say, yeah, it is going to look like all heuristics in that, like, I don't know what makes something a heuristic. Maybe it's like it is a suboptimal. Also, I was going to say there's maybe one thing that people use to mean a heuristic is it's like it's not perfect. Like it doesn't generalize to all instances, right? And it will sometimes lead you astray. And like I think that is definitely true of the representations that humans and AI use, and I don't know how it could be otherwise, right? But I also think then I would say another thing about heuristic maybe in the way it often gets used, it's like, yeah, it's suboptimal. It's like the human brain invents heuristics because it would be expensive in terms of energy or time or whatever to reason fully about this thing. This is more like a humanities question to me, as well as it's like that assumes that there is such a thing as an optimal answer. And for almost everything else, there's probably not, right? Like there's just what would have been, like with infinite time and compute and stuff, like what should you have said to your friend when you saw him at the coffee shop? Like there's just not a thing, right? So it's like
Wait, I gotta do some Bayesian updating.
Yeah,
real quick.
exactly.
And then,
Exactly,
no,
right?
exactly.
So it's
I
like
totally
this-
agree.
So it's like we use heuristic in, like, the classic example would be like when there's a known bounded search space or something like chess, and you're like, oh, you
Yeah,
can't have
yeah,
explored it, so you did this heuristic. But like the world isn't chess and most things aren't that thing. So I think this is like like it probably will look like heuristics, but they're not, that's not bad, you know?
Okay, let's open it up. Yeah, Webb, go ahead.
I want to go back to the, what Leaf's original reference to your kind of Hillary Putnam moment, the elk and the, was it the oak and the elk?
Yeah,
Okay. That, one of the things that I got out of this is that it reminds me of what they say about the learning of verbs, that we learn irregular verbs in a different way than we learn regular verbs. With regular verbs, you apply a rule. Irregular verbs, you have to memorize.
Yeah.
And it seems to me that that's at the point at which what's going on cognitively is pushing in two different directions. One towards the sort of something that can be explained internally in terms of the logic of the system.
Yeah.
You're basically basic logic and reasoning capacities, but the other one pushes you outward towards the social.
Yeah.
That is to say, out towards a world that's already been pre-described
Right.
in textual terms by a long social history. And I wonder if this is, you sort of gestured towards the social and then went inward. And I'm wondering if there's a way in which following that thread can help bring the social back into the.
So, and sorry, what is the social aspect of verb learning? It's that
it cannot be generated by purely internal rational processes,
Right.
but requires forms of memorization that require you to absorb things produced under relatively contingent circumstances for a reason.
Yeah. And I mean, verb learning is and like very famous example that it's used for looking at, the kind of trade-off between rules and exceptions. But I think it is, I actually haven't closely followed the like literature, but like I feel like it would be the case that at the beginning, everything's being learned as exceptions. And then it's like the regularity pops out for some and it kind of gets voted to then be the dominant thing, right? So I think that would be consistent with what I would say is this kind of emergent structure that we would see in neural networks. It's like there's a kind of tipping point where you go, oh, actually, and I've seen some work on things like the tolerance principle. That's one I happen to know, but I think there's other theories here. That's basically there's a tipping point where you're like, actually, it would be better for various reasons to just store this rule and store exceptions rather than learning all the exceptions, right? And I think that's actually kind of consistent with what I was saying about the exceptions by kind of being primary. Like, had it not been like inefficient to do this, you would have been fine to just keep memorizing. In fact, you keep doing it. And I think it's maybe different than saying something like you are out there looking for a rule because you prefer to have rules. And then you're like, these damn things won't fit into my rules and I'll keep them as the exceptions, right? It's like and I think that, like I could see that being consistent with what we would see here. So we might find some structured subspace for the regular verbs, and then all these other ones just kind of hang around. And there, I know there's a whole debate about the kind of quasi-regularity. You might see these little other neighborhoods of verbs that they're not regular, but they have some.
Definitely in the parallel distributed processing volumes, that's the example that Remarque and others are using, right? Like they're showing that a deep neural network for the first time is able to learn irregular verb structures, sort of. Like it says tooken for a while, and then eventually it says taken, and then so it's not as celebrated or as central as the XOR solution.
Right. Yeah, but it's actually a really interesting.
Yeah. Gideon, did you?
Oh, well, one thing that I think one often hears when people are making these analogies is to say that, or like one way of dividing this stuff up is to say that, okay, neural networks are very good, or language models are very good at like roughly the things that we've picked up in the last like 70,000 years of evolution, and much worse at the, 1.5 million years of evolution before that. And I don't really know what to make of that analogy. Like, do you have an intuitive reaction to that?
Know enough about, like, what's an example of a thing that would have been before the 70,000?
Well, a lot of this
Like,
like
I don't know the
symbolic,
timeline of when,
a
like,
lot of this
language
like
evolved.
symbolic reasoning, for example.
I think you're talking about nature versus culture.
You mean like it
Well,
would have
that's
been
part of
all
it.
exceptions for the first 30,000 years of Homo
Or
sapiens
like-
and then?
This wasn't necessarily up to the exception point, although I think that there's probably something interesting to say about from an evolutionary perspective, social evolutionary perspective of the exception point, because you do have these examples, right, where like languages that have very morphologically rich features end up like once they get mixed with other languages, end up losing a lot of those features and they move into syntax, and you have like fewer of these exceptions that a community has to memorize.
Yeah, I mean, I think something that I haven't gotten to look at to enough, like a satisfying standard, haven't seen anyone do that, but that feels like it's just like this, like waiting to be dealt with, is just the fact that language models are language models, and this, like, we know this, but it like builds in such a strong bias into what they do. So I've spent a lot of time being like, oh, this is maybe a good proxy for the brain in different types of ways. And it's like hiding under the rug the fact that there's like a really damning dissimilarity, which is that they like begin from the point of operating over tokens that are meaningful and contentful. And this is like a learning problem that like evolution had to do. And my colleague Roman Feynman has a very good point on this that I advertised at CogSci, and people, it was a very hot take. So I want to give him credit in case you think it's a cool hot take, he gets credit for it. Which is just this idea that they're kind of Fodorian in nature, that it's like, if the question is like, how do people know what the set of concepts are and what their meaning is, like Fodor's answer, who's aggressively anti-neural net, is like, it's all built in. You just have a set of concepts and they're just atoms and they're just orthogonal to each other. You're like, these are the concepts. And that's actually what language models do. We're just like, you have a space of however many tokens, you can populate them with your own ground, you can associate them however you want, but you didn't have to decide to represent the world as a set of discrete tokens, which then will relate to each other. So this is like, we just gave away the hardest part of the problem to other models don't have to do this. Vision models have arguably a harder time to diffusion models. And, LLMs are the workhorse of modern AI. Like, you're not seeing a model that's trained on vision then being supplemented with language. It's like all the multimodal models use language as a starting point. And so there's like there's something there that's pretty profound. And yeah, if like that's going to mess up these and telling us anything about human cognition, it's because like we gave away 99% of the game and then just at huge scale.
Yeah, huge scale.
Thank you very much. I learned a lot, but I am a person that lived more than a half of my life in the previous century. So my question, my kind of knowledge is from there. And but still, it's in pre-pandemic era. I read some article in New Yorker about some warehouse where already they employed robots, and they gave these robots instruction to they just deliver from warehouse to some place the items to as soon as possible from warehouse. And what these robots start to do without any instruction, they start to put everything in absolutely chaotically through the whole warehouse. And then the closest robot to this particular needed thing took it and bring it. In human thinking, that best thing is put it structurally. Yeah. For them, they don't have problem with memory. Yeah. That's the first thing. We have memory. So maybe this is one of them kind of real difference they don't have problem with memory. They structure something differently, absolutely chaotically. And probably they need to do it by themselves somehow without this our investment, trying to regulate it, trying to understand it. Probably it's something for us can be different.
Yeah, I think that's a very cute anecdote that I think illustrates the
It's not
point.
anecdote, it's
Yeah, I like that,
absolutely- You probably find it.
Yeah, I'll look that up. That's really, and I think, so I agree with you with a caveat. So I'd say like, it's true that models don't have nearly the memory limitations that humans have, but they don't have infinite memory. And so there's two, like I have some colleagues in neuroscience in particular interested in working memory. And so we've been looking at a few directions here, and I've seen other work. I just saw a similar work, and I'm trying to remember who it was. So I can. But there, so one thing we were looking at was like in a transformer. So in a model that in principle has random access to its whole context window, do you see kind of like working memory trade-offs? And you often do, which suggests that there's a reason that you might have this kind of memory problems that you don't have to physical space. It's that there's like learning and management costs associated with storing everything and then having to do it. So they language models might hit this point much higher than humans, but it doesn't mean that they would never hit it. So they'd still be subject to these kind of other constraints that aren't just like architectural or like you just don't have space. And then it's also, I think a related point is that there's this idea that there's maybe a trade-off between generalization and like efficiency or storage. So, and that's probably related to the first point. So it's like, whereas like, yes, the model in principle could memorize everything. If it does so, it won't do well in new tasks. So that's where you would see, again, a pressure to basically forget some stuff in favor of generalizing better. Now, this argument people push back too, because like it could do both. It could both remember exactly and also store a generalized representation of it. And maybe it could do both of these things. And maybe, but I think in practice, we are seeing that models actually do make these kind of compromises that it seems like they're not forced to purely by space. And so it suggests maybe
But some of those trade-offs are coming from design decisions, right? And like
Right.
use cases, like
Right.
if you do that with a foundation model, fine. And that would be really interesting to me.
Yeah.
But if you do that with a reasoning model, the reinforcement learning will be part of the effect, won't it? Like, because you're kind of already asking it to make that trade-off.
Totally.
So I don't know, like if you're doing interpretability research, you would have to compare those two against
Right.
each other.
Yeah, for some
Because
of
we're
these-
getting software now, and the software is all packaged in a way
Yeah.
where the tasks are
Well,
predefined, basically, right?
Right. For some of these like
the limits
cognitive
are
questions.
there on purpose, is what I'm
Right.
saying, right?
I mean, for
Yeah.
some of the cognitive questions, for those ones, we were just training little transformers from scratch on little toy tasks. And
Yeah,
you can
good.
even
Yeah,
observe
yeah,
the
okay,
trade-offs there.
good. Oh,
But
you
yeah,
can, yeah,
yeah,
okay,
you can
good.
observe them there.
Okay.
I think it's like, yeah, but it is true. Yeah, there's like, it's hard to say how much of it is built in, or like, even when we were finding some of these kind of what seemed to be these like working memory or other human-like patterns in LLMs, say, you're like, is it that the model has this problem, or is it that humans have the problem and they generated language and the model has to reproduce the language generated by humans, which had the problem. And so therefore it learned to have a problem. Like, so like we were finding with this locality thing, right? Like they can't go too far back in their context. And that's because they probably never had to in the data, because humans can't go too far back, that kind of. But I think, yeah, it's weird. I mean, obviously there are some constraints that humans have that LLMs don't, like humans just for like chemistry and physics reasons can't have an arbitrarily sized brain. Like you couldn't have evolved to have a huge brain because maybe you just couldn't have gotten the nutrients to support such a thing.
Speak for yourself.
Right. And so that has to matter at some point, you know.
Absolutely. Yeah, Andrea.
My question is really about whether you identify the homomorphism between thinking and understanding. Right? So these are two interrelated problems, but they can also be disentangled in meaningful ways. One of them, in my opinion, is to focus on mistakes. Right? I mean, you know, if I make certain mistakes, it becomes dubious whether I'm understanding what I'm saying in the first place. Right? If I say, oh, yesterday I attended Liv's talk and he was talking about his book on Dante. right? I mean, it becomes dubious whether I understand who Liv Weatherby is or who Dante is, right? At the same time, I'm thinking, right? So there is no doubt that I'm thinking. So do you see any sort of like a point when, this isomorphism between thinking and understanding may kind of be, I don't know, weirded out by the injection of mistakes as kind of a form of an exception?
Right. Yeah. Yeah. I mean, all of these words, I don't want to say I don't like them because I use them just so freely, like all the anthropomorphized words, and it's because like I don't want to see us invent like some stupid jargon that's not going to help us get forward. But at the same time, I think it is the case that like all of the words are like under active revision. I often put scare quotes, and I've had arguments with people that are like, why are you doing all the scare quotes? And it's like, I feel like it's annoying to not put the square quotes because we should be acknowledging how much this definition of this word is under revision. But yeah, so I guess like there's a version of thinking that's just like into processing and maybe is not controversial, right? So you'd be like, the model thinks because it runs some computation, like that seems fine, right? But then there's a version of thinking that people use that is like somewhat tied to understanding. And in that case, I think that's where I'm like, you would want to like reconcile against what humans are doing. So yeah, like you were basically saying like you were thinking because something happened in your brain when you said this thing. And yeah, I guess I don't have a good answer to this. I agree that there's like a slipperiness between those. I haven't committed to any particular relationship between thinking versus understanding, but just to say every time we use these human-y words, I think we're trying to do is get at something about mechanism. And when in asking the question, what we're really kind of interested in is how human-like or not is the thing.
But this is, if I may follow up for 1 second, this is why I think that, we're kind of navigating a very strange moment, precisely because, we apply our ordinary understanding of words, such as thinking and understanding, to a system that is not a simulation of thinking and understanding, as we're pointing out, but functions more like an analogy of thinking and understanding, right? But at the same time, it's almost as if there is an atavistic behavioral pattern that belongs to, our way of using language in relation to those two very fuzzy and blurry concepts, right? And so this is a kind of when things get a little weird,
Right.
I think.
Right. Yeah, I've been very inspired by this kind of idea of like conceptual change, that this is what happens when you're in a scientific and technological revolution. Like you see words, like words kind of are like your cue that you're in this paradigm shift, right? So it's like the words made sense before the paradigm shift. They're not going to make sense anymore after, or you're going to need new words, or they're going to be radically redefined. And during the paradigm shift, you're just like, I don't know what to do with this. And you can feel all the tension, and people get mad at each other about it, right? There's this big fights about like, how could you possibly say, like, and at the same time, you're like, but what else would you call this thing? Like, it's not just that people often put the word mere in front of it. Like, it's not just like mere pattern matching, or like, it's clearly something more than that we can all. And so I think hopefully we'll just see that we'll settle into some new, like language will step up to its job and we'll settle into some new conventions for meaning. But we're just right now, there's like a disconnect between what we were trying to refer to with the old thing, the set of things we now need to refer to. We can tell that they're not the same, but they're, it's a mess, yeah.
Hi, I'm Or Rosenblum. I'm visiting. I'm a historian of ideas, coming from. But I wonder, also picking up on what you just said, if you think that this kind of understanding of this technology of how AI thinks shifts also the way humans think, and in what way? Not about linguistics, but any other substantial way we might.
I'm very interested in this question. Like, I feel like it's not actually my expertise, and I would love to talk to people who are working on this. I'm hoping a little bit that Aria will pull some people who work on this kind of thing, because like I would have to guess yes, like it will have to. I mean, even like more mundane things change the way world, right? But it does seem like this is an existential thing of like properties that we have identified with, and are like baked into our development, like social interaction with communities and caregivers and stuff is like key parts of childhood development, right? So like these are things that we have evolved to take for granted as like a key part of thing, and that's like, so I can't imagine that this would not have an effect, right? And I don't know if it's like it might probably kind of worse in the short term, but then we could like unlearn it, right? So like one thing I've been like a simple thing that you can imagine is like, will kids right now be just way better at detecting AI generated text than us, right? Like we've evolved to look for certain kinds of cues to say this is what human text and AI text looks like. And now we're suddenly thrown into a world and like it's too late for us to like figure this out. Although maybe we'll figure it out soon. But like for a kid growing up in this, they might just be like hypersensitive to the nuances of communication, those things we can't even pick up on, right? And then we can mark ourselves and make it much easier. Like our language will shift such that we can recognize when we're having an. I think like you'll probably see communicative behavior and stuff. You'll see learning behavior change when you have access to different kinds of information. And I don't know. So I imagine it'll change us. Hopefully not for the worse. I would love to talk to people who have like who work on this either from the developmental standpoint or from the evolutionary standpoint or cultural standpoint.
It's a bit of a different direction. When I saw your first title, I was obviously thinking Turing paper. 1950, you know, instead of does a machine think, how would we know if it does? Literally the move from the Turing paper. Anyway, it's great. Highly recommend to everyone. But I've been wondering for a bit whether we're actually, as NLP, like going the wrong direction with looking at only. And I think Beck-Interp is sort of a reaction to that decision that NLP kind of implicitly made when we were doing bake-offs and all this. And that was like really very social anyway. We did bake-offs with some number. It was like, does the model reach this level of behavior at NLI, our little task? And if not, then we can get everyone together and we can like try to push it and get to that number, and then we can have a big party or whatever, social science stuff. But like, to me, I'm like, that's kind of insufficient. And it's been insufficient for a long time. Nobody trusts the benchmarks. Everyone knows this. And yet everyone wants you to make them more of them all the time, quicker, better. And there's some like thousands of arguments about quality and whatever. And so for a while, like maybe 3 years ago or so, before the Beck-Interp thing, I was like, maybe we need a new version of eval that is both output and some sort of restrictions on how you get there, which I think is sort of implied by your title. And what would that exactly look like? Well, it could be that you require the output to be at some level, but you also require that some representations underlie how they get to that output. So I was doing a project recently with Guy Davidson, who's actually here on Facebook, or no, here at NYU. Then he came with me on Facebook, and then he left again. Following up on some of Eric Todd's work on function vectors, trying to ask like, is there some shared task representation, like analogy? And the answer, like every time we look, is kind of no. The answer is like ish, a little bit. And some people have full empty will be like yes or no. But like it's never very knocked down. And so you can't actually make this an eval requirement, I think. And so it just kind of doesn't fix the problem that we might have gotten from the Turing test where we're over indexing on this behavioral output stuff. So I've been wondering, like, do we really need to dump that entirely? What do we do with this? I've been rereading this paper that actually Turing Swifty was reacting to by this guy, Jeffrey Jefferson. But and actually he has an interesting thing about parrots. I was going to tell you. I thought the parrots thing came from Descartes. Maybe everyone else. Anyway, like he was kind of saying we can never really have any understanding of whether something based on the output has a mind at all, which is but it seems to me that kind of the crux of all our understanding problems might be coming from this move that maybe was a mistake. I don't know how to fix it, but maybe you have an idea what else we could have done or what's wrong with the Turing test.
Yeah, no, I don't. So yeah, I think probably for like we both worked on eval around the same time and had a similar thing. And I think when I switched it to Beck-Interp, I was like, I'm not doing eval anymore after having a few times of like trying to come up with like the really hard task and just seeing that this feels pointless for the reasons you said. And then I actually think kind of the problem I would say in this space right now is the science is not ready to give what the practice needs, which is how do we know, like if the benchmarks aren't good enough or they're broken or they're not measuring the right thing, how do we measure? And we don't know because of the thing that we don't know what it is we're looking for. So even like like it's really, the mech-interp stuff is great to try to figure out what the representations are, but we can't actually make a prescriptive judgment on them right now, right? And this is where I'm like, maybe if we knew what humans were doing, we could, I mean, it's going to take a while. It's like once we solve cognitive neuroscience, then we can come back and say you should do that thing. But then it's not even clear that we would want that thing, right? Because maybe you want to do better than humans, or humans are heuristic in various ways. So it's like, we're trying to, like, we hope we can find some like broad principles that say, like, if you're trying to be an intelligent system, like, it will just be the case that you have to obey some trade-offs. Like, this is like the ideal thing that I could imagine the work leading to, is like, there are just some trade-offs between, say, memory and generalization that any intelligent system will have to obey. And then you could say, you're going to try to say you want to go along this curve optimally. Like, that seems like something you could imagine. But we're not close to being able to do that, right? Because we would be like, how would you even know what that thing is? And how would you know that it's, you don't, at best could have 2 points along the curve, like the humans and the LLMs, right? So I think there is a version of saying, like, we want a theoretically based evaluation, but we don't have the theory. And theory just takes the time it takes to develop. Like, you can't, no matter how much money industry has, you can't like get your eval team and say, make the theory, make the eval, do it by the end of Q2 or whatever, right? Like, it's not going to happen. So I think that's like where we're seeing the tension. Yeah, and I might just not be creative enough, but I don't think there's a short conclusion. Like, I think you just, like, people just making the best evals they can come up with is basically.
When OpenAI released O1 before the DeepSeek, or O3 before DeepSeek, whatever it was, they were talking about it anyway. Melanie Mitchell said something really interesting about this, which was, she said, because it was like that system did better on Cholet's puzzle benchmark, you know, like, or whatever it's called, than anything had ever done. It was 86% intelligence. And she said, but to get those things right, it needed to spend like $10,000 worth of tokens per answer. And she just said in her Substack, like, maybe one of the things we need to think is that, like, we think that like intelligence can't require $10,000 per correct answer. And I wonder,
or like an intelligent system would be like, this is not a good use of my money. I will go spend it elsewhere.
Well, I wonder if like token restrictions, like you would say, like, instead of benchmarking, expect to get a ton of wrong answers and say, where does the right answer come when you set a level, right? Like back engineer from that way. I don't know. I mean, this is not my area.
LLM is kind of like that, right?
What is it?
This challenge called Baby LM, which Tal is actually also.
Yeah.
It's like you get some number of parameters, some number of data points, and then a bit. But that's not going to really, I don't know. That's limited impact on the world.
Well, the other thing I would say is that this kind of jumped out at me is that when you said this theory thing just now, I was thinking, like, the reason that the unknowns are on the behavioral psychology and the neuroscience side is that they don't have theories, right? Like, they have a ton of data and there's descriptions of that data and there's math and there's kind of like a way of looking at it. But the idea that there is a fit between data and theory in either neuroscience or psychology in those areas that we're constantly drawing on to think about what thinking is laughable. So I think that, like, this challenge, this puts us in mind of a really big problem about reasoning, which I think is just to repeat your point.
It would be nice if, like,
I think that's Remainder humanism you just described.
Well,
it would be nice if, like, the presence of AI has this effect of serving as like this grand challenge that unifies, like, kind of pressures some of these disciplines to like talk to each other more and like say, like, let's stitch up our results together and see if we can figure out what's going on. Like this, like
that could be worse. Like, no, I'm just saying, like getting everybody to compromise is not always the right way to, I'm not sure the wisdom of crowds is going to do it for us.
Let's get everyone in a room and be like, okay, no one's leaving until we've come up with the grand theory of everything. And it goes everywhere from philosophy down to systems neuro.
Just more Macy conferences. That's all. Well, okay, I think we're going to leave it there because we're at time. But Ellie, thank you so much. This was so great.